Welcome back to my favorite people. Last lecture, briefly, I introduced the nucleophilic substitution and elimination reactions. And in this lecture, I'm gonna go through the reasons why alkyl halides do such reactions, and also what are those reactions. And I want to go a bit more in depth. Okay. First reason for elimination or nucleophilic substitution is that carbon is attached to electronegative element like chlorine, fluorine, bromine, or iodine. And as you see, in this case, electronegativity of chlorine is 3.16, is way higher than carbon. It means chlorine is going to steal plenty electrons and electron density from carbon. So we're going to have a good positive charge on carbon. And chlorine, it will have a negative charge. Remember, chlorine does have 3 lone pairs right now. And carbon will try to replace those missing electrons by pulling some electron density from hydrogen. But if you look to the electronegativity of hydrogen, it's not that far from carbon. It's 2.55 55 versus 2.2. And so I'm going to say amount of electron density that hydrogen will give to carbon, not that significant. So under any condition, carbon is going to have a positive charge. Okay, and we'll be looking technically for replacement of missing electrons. And where we can find those electrons or replacement, we can find them on the nucleophile. And the nucleophile has a lone pair, and those 2 electrons can be used to give the electron to carbon and kick halide out of the system. Okay, so one reason carbon has a positive charge. The second reason is the leaving group by itself. Okay, a leaving group, you need to ask yourself what will happen to the leaving group. Is it going to be stable by its own? And if the answer is yes, then there is a driving force. We are getting more stable particle, and this is the reason reaction is gonna happen. Okay, let's review how how to predict whether the leaving group is going to be stable or not. First, okay, we said size of particle to the right side of periodic table, size decreases. Down in any group, size increases. That's one. Electronegativity to the right side of periodic table, electronegativity increases. Down in any group, electronegativity decreases. Okay, so based on size, we know fluorine is the top of the group, and then chlorine, bromine, iodine. Iodine is going to have the biggest size, and then bromine. After that one, we will have the chlorine, and we will have fluorine. Electronegativity, it says fluorine is the most electronegative element. Then you will have chlorine, bromine, and iodine. Okay, that's a trend for electronegativity. And what was the electronegativity? Is the ability of pulling bonding electrons to yourself. Okay, and here, like, the size is just simply I'm comparing the technical radius of the elements or size of elements versus each other. Okay, next. Okay, now if you can reduce this ratio of charge to volume, if you can reduce ratio of charge to volume and drop this one, then in that case we say you will get more stable leaving group. Okay, so anything that's dropping the ratio of charge over volume, it will make the species more stable. Okay, let's talk about, for example, HCl. Okay, sorry, the HBr, that HI versus HBr, then HCl, then HF. I want to know what's the strongest acid in this case. Strongest acid is going to be HI. And why? Okay, 2 reasons. First, okay, if you take HI and react it with solvent, it will turn to hydronium ion plus I minus. This is going to be the acid. This one will be the base. And this one is going to be the conjugate acid. Last one, it will be the conjugate base. Okay. Two reasons HI will be the strongest acid. First reason, you have iodide is going to be the biggest element. Okay. When you attach it to hydrogen, it will, okay, if this one is iodide, it will have the biggest HX bond. Okay. So the HX bond, it will be the biggest for HI, and then HBr, and then HCl, and then HF. Okay. And so that means breaking this bond, breaking HI bond is easier. Okay. And because it's easier, I'm going to say the bond. Okay. Bond dissociation energy, the bond dissociation energy, the energy that I'm going to spend to break this bond. For HI, it will be the lowest, and then HBr, and then HCl, and then HF. So HF is going to cost me the highest energy. That's okay. One, I need to break the bond, and HI costs me the lowest energy. Now, what will happen to the molecule after breaking this bond? Okay, we have two electrons. Those two electrons, okay, they will be taken by iodide. And what do I get? I get this species. Okay, that is an I. I'm gonna say this is I and I minus. What does it mean? It means we got an electron. Okay, iodide has the biggest size. Okay, biggest size than any of this element. Okay, so iodide, because it's too big, it can easily accommodate the negative charge. So we have a -1 charge divided by volume. Okay, and volume of iodide is the biggest one. Charge is not changing. Only thing is changing is the denominator, the denominator, volume. And I'm telling you, volume of iodide, because it's the biggest volume of iodide, it will be the biggest one. Okay, so the smallest ratio for charge over volume, it will be for iodide, and iodide will be way, way more stable. Okay, so those two reasons why iodide is the most acidic acid here. One, we have a bond that we can break it easily because it's bigger than it's the biggest bond. It will be easier to break it. You spend less energy. The second thing, after you get a conjugate base, you need to ask yourself whether that conjugate base is stable or not. How? Look to the charge and compare it, and also compare it with the volume. Okay, I have a charge -1, and how about the volume? Volume is the biggest for iodide. So that means we can easily distribute it over that charge, over that volume, without creating too much repulsion. And why fluoride, that is the most electronegative element, is the weakest acid here. Fluoride is too small. Okay, so what will happen if it's too small? Okay, because fluoride is too small, this is going to happen. The new electron that is coming to the system, and the one we're stealing from hydrogen, is going to see electrons of fluorine. So that new electron is going to feel too much repulsion. Okay, too much repulsion. So that electron, okay, that electron is not going to be really that welcome. Okay, system, it will be unstable. The ratio, okay, ratio of charge over volume is going to be a big number, and because it's a big number, this species, it will be unstable. So the conjugate base, it will be unstable. And if it's unstable, it will react. What does it mean? It will steal hydrogen from the environment, or it will go and it will get involved in a chemical reaction. because fluorine wants to share electron with something else just to get a stable, get rid of technically this negative charge as soon as possible. Okay. So here, based on this table, as you see, acids that they have the lower pKa's, they are going to give us the best living groups. Okay. And for example, HI is going to give us H plus and I minus, or say HBr will give us H plus and Br. Okay, these two species are very stable. Okay, those two are very stable. So I'm going to say because they are stable, they will be happy. Okay, so stable conjugate base. Okay, stable conjugate base means good living group. Okay. So anything that makes the conjugate base more stable, it will turn it to a good living group. Okay. And how about this compound? So imagine you have such a compound. Okay. I have a methyl and we have if you take hydrogen from it, it will turn to such a system. Okay. Now we have oxygen. Oxygen is going to take those 2 electrons, and oxygen is going to have 3 lone pairs. So this one will be -1. Okay. This group, the name for it, we call it tacetylate, and we show it by OTS. Okay, OTS is really good living group. Okay, why OTS is such a good living group? Because the negative charge on oxygen, it can be shared by, okay, let's call this one 1, 2, and 3. It can be shared with those, oxygen, number 2 or number 3. And so technically, you can get such a resonance structures. Okay, so let me here copy paste them. Okay, so I have one resonance structure that's -1. The second resonance structure, let's make it double bond here. We will have only 2 lone pairs there, and that means this one will be gone, and the negative charge, it will show up on this oxygen, and that one will be -1. And next one, again, I'm gonna make a double bond here, and I will break this bond and put the negative charge there. That's going to be -1. So as you see, I got 3 resonance structures. Okay, and anything that distributed the positive, the negative charge, it will make the system more happy. And so technically, you can say ratio of charge over volume got down. And if that one got down, system will be happy and it will be more stable. And this is the reason tacetylate is such a good living group. Okay. And again, let's go back to the table. And good living groups are conjugate base of strong acids. Okay, strong acid. And if your acid has a high pKa, then the conjugate base, it will be unstable. Okay. For example, look to this one. Okay, this says unstable. And for example, for ammonia, if you turn it to NH2, NH2 is really unstable conjugate base. So this NH2 is going to go after a chemical reaction, and it will try to get the hydrogen back as soon as possible. So higher, and then less stable means more reactive. And if it's more reactive, that's not going to be a really good living group for us, because why on earth you want to make such an unstable species? Reaction is not going to go on that direction. So if your living group is not stable, okay, you'll have hard time to kick it out of the system. And species like, species like, say, hydroxide, fluoride, or methoxide, okay, or alkoxide. Alkoxide, okay, alkyl, okay, alkyl groups that they have oxygen, okay, and in that case we call them alkoxide. Alkoxide, so there is an oxygen attached to alkyl group. For example, this one, or a tertiary that it has oxygen and with a negative charge. Those are really unstable. And because they are unstable, they will be strong base, okay, strong base. So you have a weak acid and you will get a strong base. Strong bases are not good living groups, okay, are not good living groups. And now what will happen if I turn it to, say, a neutral compound, okay? If I, for example, my living group is turned to a neutral compound like water, that's perfect. And that system is going to be stable for long time, and nothing will happen to it. And so if you can turn it to water or to species with a zero charge, that's perfect. But if you manage to turn it to a species with a negative charge, and that negative charge can be distributed over a big volume, and that's even better. Thank you very much, and I'm going to start the lecture here.